Okay, in this video we're going to, this is mathematical logic in the propositional logic sequence, and we'll be talking about semantic properties. Okay, I am going to state and then basically not prove, because the proof is so easy, this proposition, which is basically telling us that the value assigned by a truth value assignment to a sentence is determined completely by the truth value assignments to the atoms that occur in the sentence, right? So, for instance, right, if we were going to try to, determine the, so imagine that we had the truth value assignment, V, for which it takes any sentence and assigns it, any atomic sentence. So you take any atomic sentence and assign it the value true, right? So this is a completely boring and constant truth value assignment. We want to evaluate the sentence, right? Figure out what the value of, if P1 then P2, right? Figure out what the value of that is. We don't need all of the atoms, right? We only need the atoms P1 and P2. That is effectively what this theorem is telling us, is that when you have a particular sentence and a truth value assignment, you only need to know what are the assignments that it makes to the atoms that occur in phi, in the sentence that we're dealing with. Now, the formal way that we're going to express that is to say that if you give me any two truth value assignments which agree on the atoms that occur in phi, they will assign phi the same assignment, right? So that is effectively telling us that as soon as you determine the values received by the atoms in phi, then the value that phi receives is completely unique. So since this is fairly clear, and if you just write out the proof by induction, it all kind of just falls right out, so I'm not going to bother proving that. For the next part, we're just going to discuss a few definitions. And my notation is going to diverge from the books, in part because I'm writing things in a simplified version of LaTeX that works in a web browser called Katek. Anyway, long story short, I cannot in an easy way render the symbols that Hinman uses in his textbook, so I'm going to use other symbols that are also somewhat more standard symbols anyway. So in any case, so I'm going to write this double turnstile for what we're going to call semantic consequence. Hinman uses a triple turnstile. So the sort of correspondence is not too hard anyway. Even though I'm using different symbols, they're not radically different symbols. Anyway, so we're going to say that a sentence phi has psi as a semantic consequence, right? So often this is read as phi entails psi. And what that means is that every truth value assignment which satisfies phi must also satisfy psi. Now here I'm using the word satisfy. When I say satisfy, I just mean that the value of the assignment is true, right? So that's what it is for V to satisfy phi. So again, just to say it again, phi entails psi if and only if every truth value assignment V which satisfies phi must also then satisfy psi. That's what it is for this entailment to hold between phi and psi. Let's see an example. So if we take the sentence, if P1 then P2, I claim that this entails, in fact it's equivalent to, but we'll get to that later, this entails the sentence negation P1 disjunction P2. And by the way, notice I am now writing things in infix notation, which we really take to be in a sense like syntactic sugar for prefix notation. So just remember, know that formally, technically, we're taking all of this to be prefix notation. So every time you see the infix notation, we are technically sort of rewriting that in our minds as prefix notation, and all of our claims are really technically in prefix notation. But anyway, okay. So let's show this entailment, right? So in order to show that P1 arrow P2 entails negation P1 disjunction P2, I need to argue in the following way. I take any V, which is a truth value assignment that satisfies the first sentence, P1 arrow P2. I take a V which satisfies that sentence. And then what I need to do is argue that this truth value assignment must also satisfy the other sentence, which in this example is negation P1 disjunction P2. So with the assumptions that I've made, I need to argue that V satisfies that other sentence, negation P1 or P2. Here's my argument. Well, since we know about V that it satisfies the arrow sentence, and by definition, right, by the semantics of truth value assignments and the arrow symbol particularly, we know that either one of the following two holds. Either P1 must be false or P2 must be true. That is simply the definition of a truth value assignment assigning true to some arrow sentence. Now, let's argue by cases, because this is an or sentence. We're going to argue by cases. So to show that, if the former is true, if the value of P1 is false, then we can immediately infer that the value of negation P1 is true, and then because of that and the semantics of disjunction, we have that the value of negation P1 disjunction P2 is true. Oh, sorry, I'm missing that from the slide. It should say equals true. In any case, it's clear what I'm getting at. Sorry about that. And then we argue in the other case, and again, I've neglected to write equals true in that case also. But right, if we're in the other case where P2 is true, right? So I'm now imagining this other case, V of P2 equals T. And if we are in that case, then immediately from the semantics of disjunction, the value of the disjunction is true. So basically the upshot here is that no matter which case we're in, the value of negation P1 disjunction P2 is true. And that's what we wanted to show. Okay, the next definition, and these are all, by the way, semantic sort of concepts, right? So they're concepts that basically that are stated in terms of truth value assignments. So we're now going to define equivalence. So a sentence phi is equivalent to psi. The way the book states it, which is perfectly good, is that every truth value assignment which satisfies phi also satisfies psi, and vice versa. It's worth pointing out that we could actually just state this in terms of consequence, which we have already defined earlier. So phi is equivalent to psi if and only if phi entails psi and also psi entails phi. So these are, right, these two definitions really say the same thing. It's worth seeing it in two different ways. Okay, and finally, tautology. So again, the book defines a tautology in a perfectly good way. It says that a tautology is any sentence for which every truth value assignment assigns it to true. So an example, just to be clear, an example would be like negation P1, right? This is what I will call the canonical, sorry, not that one, although that's fine, but I will generally call this the canonical tautology, right? It's just one of the simplest available tautologies, P1 disjunction negation P1. And if you give me any truth value assignment, all I need to know is the assignment it makes to P1. If it makes P1 true, then this part is true and the whole thing is true. If it makes P1 false, then this is true, and therefore, again, the whole thing is true. So it's a very simple disjunction, and so I'm going to refer to that as the canonical disjunction. But in any case, just as the book has one definition, but it's nice to see another definition maybe stated in terms of language that we already have, we could say that a sentence is a tautology if and only if it is equivalent to the canonical tautology, right? So all tautologies are equivalent to each other. And so in particular, we could take them to all be equivalent to that one, the canonical one. In fact, we don't even need total equivalence because it is actually enough if the canonical tautology entails our sentence. Even that is enough to know that, that the sentence is a tautology. And here I'm just remarking that I have the canonical tautology as written above, and when I want to abbreviate it, I'll abbreviate it with an italics T. So the sort of like straight up T is my symbol for the truth value, and my italics T is my symbol for the canonical tautology. So this italics T is actually a sentence, not a truth value. And since I'm already talking about the canonical tautology, I might as well talk about the canonical contradiction, which I take to be P1 conjunction negation P1, and I will write that with italics F. The following is a collection of facts that are not too hard to prove, so I will just state them as and claim that they are worth knowing, but the proofs should be quite easy. From our definitions, phi is equivalent to psi if and only if the biconditional sentence, right, phi biconditional psi is a tautology. So it's worth, right, like, so the left-hand side, phi equivalent to psi, is a kind of a statement in the sort of semantic language, and, you know, this other thing uses the formal language of the biconditional. Okay, we're also saying that it's a tautology and that's a semantic concept. So I mean, of course, right? Anyway. So it's worth knowing that equivalence is captured by this sort of like the tautology of this sentence. Okay, another similar such statement, right? Phi merely entails psi if and only if the single conditional direction is a tautology.